All right, so we're going to talk now about the nervous system, and we're going to start by talking about our central nervous system, which is our brain and our spinal cord. And then after that, in the next video, we'll talk about the peripheral nervous system, which is everything outside of our brain and our spinal cord. So central brain and spinal cord, the central refers both to the physical location, so the brain and spinal cord is center in our body, but also in terms of how central these are to our function. And nerves, as I think it said in the previous slide, nerves are just bundles of axons and neurons. Axons and dendrites rather, and our spinal cord is essentially a bundle of nerves that is surrounded by bone to protect it. That goes down the center of our backs, and it's the main communication pathway between our brain and the rest of our body. And most of you, I'm sure, know that if we injure our spinal cord, we disrupt that communication. And so we either get paralysis because the motor neurons are damaged and can't send motor messages below that point. But we also get damage to the sensory neurons at the same time, and so we also have numbness. We can't get messages from our body to tell our brain what we feel. You and I, right? Your book talks a lot about specific brain areas, brain parts. Your monster assignment gives you specific brain parts to think more about, and I'll make those available to everyone, so everyone can read everyone's stories. But we are going to focus, and the thing that I think is most important for you to understand is that our brain has kind of a three-part organization that is really useful to think about. And this is an evolutionary and a function organization. And it is from the bottom up. We're going to go from what is oldest in terms of evolution and most basic in terms of function to what is newest in terms of evolution and more complex in terms of function. And the other thing, and there's a video for you to watch about this, is that as we talk about all of these parts, it's important to understand that we have a left brain and a right brain, or a left hemisphere and a right hemisphere, with a corpus callosum that goes down the center of it, which is just a bundle of nerves that is to connect those two hemispheres so they function as one organ. There's a really important video to watch about what happens if we sever the corpus callosum, and it tells us very nicely what the two halves of our brain, what unique jobs each half has. So make sure you watch that after you finish this video. So I think, this evolutionary context, if we look at the bottom, at the hindbrain, or the brainstem, the midbrain, or the limbic system, and then the forebrain, which is really our cerebral cortex, and we'll take these one at a time, starting with the one that is oldest. So our hindbrain, our brainstem, is the oldest part of our brain in terms of evolution and the least sophisticated in terms of function. And so what this means is that that we share the same parts, as you see them labeled here, and the same functions with lots of other animals. And so if we even animals as distantly related to us as frogs are going to have a brainstem that functions and has the same parts that we have in our brainstem. The brainstem and the hindbrain, I'm going to use those terms interchangeably, is about immediate life support. If something goes wrong with your brainstem, then you die. Ironically or paradoxically, when we talk about someone being brain dead, what we mean is that only their brainstem is functioning. And so their heart is continuing to beat, they're continuing to breathe, but all of the rest of their brain that is about behavior and mental process isn't functioning anymore. And so it's just the life-giving part that's functioning. But an injury here almost always results in death or severe impairment in some way. Our midbrain, right, in the middle of our brain, is made up mostly of our limbic system, and you can see that demonstrated here. So it's the one being pointed to. It is newer than the brainstem or the hindbrain in terms of evolution, and therefore a frog is not going to have a midbrain that looks quite like ours, but a cat or a dog will, because we share more evolutionary history with them. And it is responsible not for immediate life support, but for long-term survival and for species survival. And so here, so we have things like appetite, um, our fear reaction is here with the amygdala, our kind of memory that allows us to remember important things is here, but also our sex drive is here, and our motivation for behavior in that cingulate gyrus is here. And so lots of important but fairly basic behavioral things happen here. And then if we move up, right, to the cerebral cortex, and this is a nice color-coded image so that you can see the different parts, because our cerebral cortex has 4 lobes to it. The occipital lobe, which is back here, right, also known as our visual cortex, our temporal lobe, which is here, also known as our auditory cortex, our parietal lobe, also known as our somatosensory cortex, and then our frontal lobe, which we'll talk about a great deal. We'll take these a little bit, break this down. I think some of this we've already said, right? So the visual cortex obviously is about visual information. That somatosensory cortex is about moving your body, understanding where your body is in space, getting pain information or other information from your body. So it is very much about body stuff, body control. Whereas your temporal lobe is also known as your auditory cortex, and part of what it does is manage auditory hearing information. But it also is really important for memory and language, and also about deriving meaning from those experiences. But it's the frontal lobe where all the money is here. Our frontal lobe, all right, is here behind our forehead. And in fact, the reason we have a forehead is to accommodate this giant human frontal lobe. If you look at other animals, they don't have a forehead. If my dogs weren't sleeping, I might get one of them for you to show you. Maybe I can. Hang on a second. All right. So I've got Jax and Dakota here because I called one and they both came. But if we look at Jax's face here, you can see it, right? He's a good boy. But as I pet him, you can see that I get to his eyes and his eyebrow ridge, and then his head goes straight back, right? Eyebrow ridge and nothing. Now, that doesn't mean that Jax is not a very good and smart boy, but it does mean that he does not have a well-developed frontal lobe. Good boy. That he doesn't have a well-developed frontal lobe. The way mine, right? My eyebrow ridge, then there's a whole still lot of vertical space to accommodate my frontal lobe. And our frontal lobe is important for decision making, judgment, planning, impulse control, the deliberate use of memory, so reminiscing, projecting myself into the future, imagining what tomorrow will be like, etc. Really important for all of those higher order things that make us uniquely human. And there are some animals that have a better developed frontal lobe than Jax and Dakota. And we can tell that in part by the shapes of their heads. Elephants have more of that planning ability. Some of our sea mammals do, though they also have blowholes and other things going on in their head. And so, animals that have more of a forehead, and certainly our primate cousins, have much more of a frontal lobe going on. And then their behavior shows that, and their ability to grieve, for example, right? Grief is about memory, but also about projecting oneself into a future without the person or the loved one that you're grieving. So one of the things to think about in terms of Jax's lack of frontal lobe, or relative lack, he has a frontal lobe, just not as big as ours, is that his behavior is less predictable. If he gets scared enough, if he gets upset enough, he could bite. He is not a biting dog. He's never bit me. I can't imagine him biting somebody, but I know because he's a dog with a not well-developed frontal lobe, he could do that, right? It means that he might make decisions that are against his best interests. Like he can't easily stop himself from eating something even though he knows he's going to get in trouble for it, right? Whereas you and I, with well-developed frontal lobes, could do that. We could exert self-control in our decision making. When we get to the human development chapter, we'll talk more about the fact that our frontal lobe doesn't mature until the young adulthood, and that before that we are not very good, or at least not as good at making good decisions and showing impulse control, which is why teenagers behave very differently than young adults in many ways. But we'll talk more about that in more detail in the human development chapter. All right. So we'll finish up here by talking about the rest of our nervous system, which is our peripheral meaning to the side, right? Like peripheral vision is to the side. Our peripheral nervous system is everything outside of that central nervous system. And it has two parts. It has our somatic system, which is less interesting in a psychology class, but that controls our body, our voluntary parts of our body. And then the autonomic system is a little bit more interesting to us. It's about involuntary or automatic systems, such as heartbeat, but also it is in charge of something called our sympathetic division, and that's our alarm system. So most of you probably know the idea that we have a fight or flight response, often called sometimes a fight, flight, or freeze, because freeze is a third option. And that's our alarm system, right? And you may know that adrenaline is part of that. What you may know from your reading is that the amygdala in our limbic system is an important part of that alarm system. And that when our fight or flight response goes off, we get increased blood flow to our arms and legs, increased respiration to get more oxygen into our blood. But at the same time, adrenaline also makes it less likely that our frontal lobe will be dictating our decision-making process. And that's an important part of the fight or flight. And so sometimes, we have examples of people being in a situation where they get very frightened and then they behave in a way that they normally wouldn't choose to behave. So if you've ever been through like the haunted house at like compounds at Halloween, every year some of their staff get punched. They jump out from and scare someone, and someone, without even thinking about it, punches them, even though they know, right, that this is not a real threat. They can't stop themselves because of the adrenaline. Crimes of passion, where somebody doesn't want to kill their wife, but they walk in on their wife with another man and they have a gun in their hand and they kill them both. They wouldn't plan to do that, they wouldn't want to do that, but in the moment, adrenaline is taking away their decision-making ability. The story I always tell here is that the night my family showed its true colors, we were coming up to our front door late at night. The kids were all small. We had been out, and Jess, we were kind of walking single file from the driveway to the door, and Jess was first, and when she got up near the door, she yelled skunk. There was a skunk there, and she panicked and just yelled skunk. And then everything fell apart. Nick ran down the walk and locked himself in the car. Alexander ran after him and was banging and begging to be let in the car, and Nick was just shaking his head at the window and wouldn't let him in. I apparently wasn't moving fast enough for my lovely husband, and he knocked me out of the way so that I fell into the shrubs and ran past me. We all finally assembled in the driveway, got Nick out of the car, went in the back door, because there was another way in the house, got in the house and heard knocking and realized we had all left Jessica out in the front of the house with the skunk. None of those are choices any of us would make if we were being rational, but adrenaline made us not so rational and made us react with raw emotion from our limbic system and turn off the ability of our frontal lobe to kind of weigh pros and cons and make careful decisions. And so that is our sympathetic division. We also have a parasympathetic division, which is our Department of Peace, as opposed to this Department of War that we've just been talking about. All right, so I was saying before I got interrupted, the parasympathetic division is our Department of Peace, and its job is to turn off the sympathetic division. So, imagine prehistoric man, he's out gathering berries, and all of a sudden a saber-toothed tiger jumps in front of him. His best bet of survival is a quick decision, right? That's why adrenaline turns off our frontal lobe, that if that man was to sit there trying to weigh his options, while he was weighing options, he'd probably become dinner. And so he quickly either runs or fights, runs away really fast, fights really hard to survive. So let's say he runs and he runs and he runs and he runs and he runs. At some point, if he's outrun or outsmarted the saber-toothed tiger and he's gotten away, he shouldn't keep running because he's just using up all his energy. And if he keeps running till he collapses, he's an easy dinner for somebody else. So our Department of Peace, the parasympathetic division, it's its job to decide there is no more threat. And if there is no more threat, we can turn off the adrenaline. We can go back to making frontal lobe-based decisions. We can conserve energy and live to fight another day. And that's really important. And so often we get the advice that if we're arguing with somebody, we should walk away, but that's not enough, right? Because if we're arguing with somebody first, if your life is going reasonably well, then there aren't a lot of times that you're actually being physically threatened and need to run away or fight really hard. That most of the threats in our modern lives are, we can hear the sirens in the background. Hang on a sec. Most of the threats in our modern life, I was saying, are actually not physical threats. And so you're arguing often with somebody you love, right? But you're seeing an angry face in front of you. Your amygdala says, uh-oh, angry face, kicks in your fight or flight reaction, and then you're fighting with somebody you love, but you are not using your frontal lobe, and you are saying hurtful, terrible things that your sympathetic nervous system, the fight or flight response, is simply telling you win. Win. Your job is to win. And so you fight to win, which is not necessarily the best thing with a relationship you want to preserve, right? And then we hear the advice that we should walk away, but we walk away. And you know this, your big frontal lobe is allowing you to imagine you're still having the fight. And you're thinking about all the things you're going to say to win the fight when you get back in the room with that person. And so the real trick is not just to walk away, but to distract yourself, to convince your brain essentially that the threat is over. And so maybe that's listening to music, maybe that's reading a book, maybe that's calling a friend and talking about something else. But you need to get to the point where you're no longer thinking about the fight. The adrenaline comes down, the parasympathetic division takes over, and then you can go back in the room and use your nice big frontal lobe to have a rational discussion of what you're upset about. And so both of these are very important to the function of our nervous system. So that is it. This was a particularly long video, and I apologize for that. There is another video for you to watch about the corpus callosum. You also have the ability to take a practice test for extra credit. Just one question telling me how neurons communicate. Promise you you'll have to do that on the test. So this is a good practice to get feedback from. Okay? I'll see you in class.